Okay, this is chapter 15, lecture 1, part 1. We're going to be talking about solubility equilibria, and this can be used to explain a lot of stuff, how toothpaste works, or pigments within paint. And over here on the left, we have an X-ray image of somebody's intestinal track and so on that's enhanced by barium sulfate. Barium sulfate is a contrast agent for X-rays. Barium is a heavy metal that absorbs a lot of X-rays. And you may have remembered a lab where we dealt with barium chloride to produce certain precipitates. And this substance is very toxic. It's poisonous. It's readily soluble. But if somebody drinks a suspension of barium sulfate, this is insoluble, and it coats the intestinal tract walls. And so when you put somebody in an x-ray, you can actually image the intestines quite well. Even though it's not bone, it'll absorb X radiation pretty well. Toothpaste also, the fluoride is not super soluble, and there are certain ions that are mixed with fluoride to prevent that from becoming too soluble. Too much fluoride is bad. Too little fluoride, of course, is not desirable either. Now, when we're dealing with substances, we've talked about precipitation reactions before, but let's talk about soluble substances. Sodium chloride does have a finite solubility, and we know that when this substance dissolves, it forms sodium ion and chloride ion, and we call this dissolution. Okay, when something dissolves into a solution, we're talking about electrolytes. Okay, when this substance dissolves in water, it produces ionic ions that are dissolved in the water, so we write AQ. And this is a strong electrolyte, and when we're going from a solid to aqueous things, we call that dissolution. When we're going from ions to a solid, we call this precipitation. Okay, so it's possible, for example, to do this reaction 1 by taking some crystalline sodium chloride, adding it into a beaker of water and allowing it to dissolve. And it's also possible to do this reaction 2 if we have excess sodium ions and excess chloride ions. These can deposit to form sodium chloride crystals, and you might do that during crystal growth. It might happen if you evaporate seawater, for example. You deposit crystals of sodium chloride during that process, and this is one way to manufacture sea salt, for example. Recrystallization of that could give you sodium chloride. Now, the solubility expression is always defined in terms of the solid on the left and ions on the right. So if we're talking about barium sulfate, okay, this is barium sulfate. This is a solid substance, and it's going to be very slightly soluble, okay? So that's why we're using these equilibrium arrows. And, there's water present, and what we're forming is barium ion. Barium is a group 2 element, so its charge is +2, and sulfate is SO4 2 negative, okay? Now, this is a solid, and remember how solids don't enter into the equilibrium expression. So if we were to write the equilibrium expression for this, it's typically products over reactants. So it's going to be barium ion concentration times the sulfate ion concentration divided by 1. The activity of barium sulfate is 1, so we usually just leave that off. And we have a special name for this. This is the solubility product principle. Basically, the equilibrium is equal to the concentrations of the ions raised to the power of the coefficient in the balanced chemical equation. And we call this the KSP. Okay? So that's KSP. And that's just going to be equal to barium ion times sulfate ion. Okay? And these are going to have certain values. You want to look in Appendix J of the OpenStax book. And if we do that now here, Appendix J, it's abbreviated, let me zoom in a little bit here. It's alphabetized. So first it's alphabetized by the metal. So barium sulfate has a KSP of 2.3 times 10 to the negative 8. Okay, 2.3 times 10 to the negative 8. So this value here is quite small. Okay, and remember, if your equilibrium constants are much less than 1, that means small, the left side is favored. Okay, so that means if we added barium sulfate into a beaker, okay, of some water, we would have a large crystal, let's say a barium sulfate composed of lots of different barium and sulfate ions, and we might have just a few in solution. Okay, so these are barium ions, and maybe we have some different sulfate ions floating around. Okay, and that's of course in the crystalline structure as well. And so we call these substances insoluble in the last class, but we call them very slightly soluble. Okay. If something has a KSP of 10 to the minus 8th, it means that less than a millionth of the formula units of barium sulfate are dissolving into the water. Okay. Now you can also think about this in terms of reactions, right? So if we have barium chloride, which is aqueous, and we have sodium sulfate, which is aqueous, we know there's a double replacement reaction where the barium and the sulfate hook up here to give barium sulfate, and we have chloride ions and sodium ions. So normally we think of sodium chloride as being soluble, right? And we think of barium sulfate as being the substance that precipitates. But we now want to consider that barium sulfate is ever so slightly soluble, and some of that will be in equilibrium with very small amounts of ions, barium and sulfate. Okay? And again, we call this reaction right here the KSP, where SP means solubility product. Okay, so just remember you have the solid on the left and you have the ions on the right. In our lecture guide, we have a few other examples. Let's switch to a different color here. So we've got calcium carbonate, which is a solid, and that's in equilibrium with calcium ions. And carbonate. Okay, this is a component of limestone, and caves form by this reaction happening from left to right over thousands of years to produce hollow structures under the earth. So that's how the bat cave would be formed. So this is the chemical equilibrium. It's balanced. The coefficients are all just 1, 1, 1, 1, 1. And then what we can write is the equilibrium expression for this. The KSP is going to be equal to calcium ion concentration times carbonate ion concentration. And this is going to be equal to, if we look at Appendix J, calcium, 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 carbonate. Okay, there it is, 8.7 times 10 to the minus 9. Okay. Let's do the other one. Aluminum hydroxide. Okay, you'll notice there's a 3 there. So unlike the lecture guide, we want to do this correctly. Aluminum is in a group 3 of the periodic table, so it's going to be a charge of plus 3. And then we have 3 hydroxide ions floating around there, and they're aqueous. Okay, so that's balanced with all the charges and coefficients correct. Now, the KSP for this is going to be mathematically equal to products over reactants, right? So aluminum is, we just have one of those. So that's technically to the, the first power. And then we have hydroxide here. And there's 3 there, so we need to use the 3. Okay, so what is that value equal to? Let's look on Appendix 3. And aluminum hydroxide, there it is, 2 times 10 to the minus 32. This is a very, very insoluble substance. Okay, so that gives you a brief idea of what we're looking at here so far. Oh, let me give you some practice problems. Okay. Write the KSP, equilibrium reaction out. Let's do that for magnesium hydroxide. Okay. Then I would like you to write the KSP, mathematical equilibrium expression. Okay. And then what is the value in Appendix J? I should note that the lecture guide does not have this appendix of KSP values. All right.